My name is Juhyung Lee. In this session, I'm going to talk about vegetation moisture, why it is important for forest management and carbon mitigation. In the past 5 years, there have been a lot of unprecedented wildfires. However, they have occurred in the major carbon sink area. However, this kind of large and huge carbon emission is not usually incorporated into our carbon policy and carbon neutrality scheme. So I would like to discuss how much we are prepared for it, what we can do, what kind of things we have to develop. First, I'm going to briefly introduce the three elements required for fire occurrence and why vegetation moisture is the biggest important missing element, and why it is tricky and difficult to retrieve and estimate, extract vegetation moisture from currently available sensors and retrieval system. And I will introduce NDVI ecosystem and live fuel moisture content products, which has been retrieved with infrared sensors. And we'll introduce another forest property products that we can retrieve from L-band microwave sensors. And at the very end of this session, I will briefly make discussions and what kind of opportunities we will have. Forests are paradoxical. They are a great carbon sink, but at the same time, they can be great carbon emitters at any time. So this is kind of contradictory. For a short term, there is effect of heating in forests. Uh, and then it can make large carbon emissions. But in contrast, there's a long-term cooling effect. For this, they can sequester a lot of carbon. So forests, they play a role of a great carbon source and heat source in the extreme heat events, and at the same time, they are a great catalyst for more destructive wildfires in these dry and warm conditions. And then ecosystem enter heat amplifying feedback events. So if the fuel temperature increases, and then that automatically also increase the sensible heat, which is shown by H sub C, and fuel temperature is shown by T sub C in equation number 1. So the forests that have been a great carbon sink previously now start to transition to carbon emitters in recent warming environment. In 2023, Canadian wildfires emitted 22% of global carbon from wildfires, and this amount of carbon almost 5 times the average for the past 20 years, according to Copernicus atmosphere monitoring service. And this much carbon far exceeds the carbon emission allowed for the carbon Canada's economy, and this is triple the annual pollution from fossil fuels in Canada, and they are more than just combined emissions from 100 countries. So we'll briefly look at another data. This amount of wildfire emission is actually uh, the similar to anthropogenic carbon emission for fossil fuels in any other countries except China. China is the world's largest polluter. And in addition to Canada and Siberian taiga forests are not different. They also transition from carbon sink to carbon source. In 2024, there were third highest carbon emissions in 2 decades after 2019 and 2020. Yeah, so if you look at the figure on the right hand side, we pretty much passed a tipping point from carbon sink to carbon source. It's been more than 22 years. So if you look at in this figure, boreal forest is actually highest They lost the great amount of tree cover because of wildfire, and it's the highest tree lost because of wildfires. So indeed, they are yeah they have the highest carbon dioxide emissions because of wildfire. Even in the boreal forest region, the Siberia is experiencing very severe wildfires, and this in this figure, Sakha Republic is in the Siberia region. In 2022, Amazon wildfires recorded the highest carbon emissions in 20 years. You know, Amazon is one of the largest forest area in the world, and Africa is not an exception. In 2024, emitted more greenhouse gases than it actually absorbs, and it is mainly contributed to fossil fuel plus land change. The Northern Australia burned 84 million hectares in 2023. Considering that 2023 Canadian wildfire burned almost 20 million hectares, this is much greater amount and biggest bushfire in more than a decade. Like we just briefly discussed about the boreal forest, if you look at this chart about the extreme forest fires in 2023, Canada actually yeah, showed the highest amount of carbon emissions, which correspond to uh, the fossil fuel and industry annual carbon dioxide emission, if you look at the chart on the right hand side, almost corresponding to the India. So this much of Canadian wildfires in 2023 and their carbon emission amount is actually, yeah, this much wildfire carbon emission actually far exceeds the annual carbon dioxide emission from fossil fuel and industry in any other countries in the world except China. So if you look at the Canadian forests a little bit more closely, if you look at the figure on the top, and you can see the forests are nicely divided into managed forest and unmanaged forest. So managed forest means you can make like harvesting activities and logging in businesses, and leisures are allowed, and traveling and even like agriculture activities are allowed. However, unmanaged forest is something that people can't really access and enter, and nothing is going on there. Interestingly, they are well overlap with the fire activities. If you can see on the bottom, the fires are shown by the red color, and then harvested forests are shown by the green color. So we can say that in most of our fires are, occur in unmanaged forests, and if people make some activities or harvesting activities and some logging industry and so on, and in this managed forest, and then there were a few fire occurrence. So although loggings are often known as a huge source of carbon emissions, and but at the same time, it's very important for control of wildfires because it is a great way, because there can be one way to secure and maintain soil moisture and vegetation moisture in forest area and reduce forest density. Otherwise, if we just leave it unmanaged, and then if we too much strictly prevent any kind of activities, and that will make the forest more denser and drier, so that the trees have to make a great competition to have a moisture between the trees. So before soil moisture is completely depleted. It's completely depleted. People should be able to cut the trees to maintain soil moisture and vegetation moisture in forests. So I'm not saying that we have to make like bare mountains or bare soils. It would be ideally it would be great if we can reduce vegetation density. So that we can maintain moisture in soils and vegetation. Yeah. So just would like to emphasize that wildfires usually occur in unmanaged areas where logging is completely prevented, prohibited, and should not be. Yeah, yeah. But um, this is not really that this may not be the idea for maintain moisture in the forest area. So I think that if indigenous people could move into this area and live there and harvest the trees or make some agriculture activities, then I think wildfires would have occurred, wouldn't have occurred this much severely and frequently. So because of that, recently there has been some paradigm shift from strict prohibition of logging to selective harvesting. Fire suppression and forest management policies have resulted in denser and more homogeneous forests in Western North America, which made forests more vulnerable to pest spread and wildfire spread. So there's increasing severity of wildfires and flooding, along with protests over logging. So selective logging can mitigate against catastrophic catastrophic floods and prevent damages to watersheds and habitats and livelihood of people who largely rely on forest resources. However, the question is to make, I mean, to to allow in order to allow the selective logging or harvesting, we really have to know when and where we have to, cut the trees. And that is, that's something that we don't know yet. So if you look at the figure here, which shows the three elements needed for fire occurrence, and we need oxygen and fuel heat. However, there's a lack of near real-time observations for the fuel conditions and the heat development. So we don't know which forests are under, cooling process or heating process. So we don't know where and what uh, when to cut the trees so far. And the fuel moistures can be a good proxy of fuel development and heat development. And by the definition, fuel moisture is the measure of the amount of water in fuel and available to the fire, and express it as the percentage of dry weight of that specific fuels. And currently, while fuel fire fuel information is modeled by weather information such as humidity and precipitation. So, for example, if we have this amount of precipitation and humidity today, and then what would be fuel moisture we would have tomorrow? This kind of relationship. So ignition and large-scale spread of wildfire really depends on this fuel moisture and weather conditions. However, weather conditions such as wind or rainfall is non-manageable resources. However, we are able to manage, relatively speaking, like forests as a fuel. So there's some potential to control this cycle. So at the moment, due to a lack of near real-time observations of fuel moisture and fuel conditions and vegetation heating, we actually rely on evapotranspiration rate, which can be an indirect proxy of fuel moisture. So what do we expect to monitor from fewer moisture. So if you look at this fire development figure, this is as temperature increases, fire development undergo several different type of phase over time. There are three phases: preheating, fuel, and combustion and extinction. So when as temperature goes up, the fire start to enter and experience fuel preheating, and they finally reach combustion stage at maximum temperature. And then as temperature gradually decreases, we're gonna end up with extinction. So the current modifier products pretty much detect this area in green box, and by looking at their color after ignition. And when we talk about fewer moistures, we try to focus on this fewer preheating stage in blue box. So before actually having combustion and ahead of any flaming, we try to detect the increase of temperature and monitor preheating process to make a prediction for the next phase, which would be combustion. So what's going on in the pre-ignition phase? It's like I said, it's a preheat. It's preheating. It's a preheating process. During this phase, vegetation reach a temperature um, at which it can start to ignite. As the vegetation is heated, it often loses water. This is the basic phenomena rationale of uh, of this approach, so that as it loses water, we can indirectly infer the fewer moisture. Yeah, fewer moisture. So as the vegetation is heated, it loses water, and fewer moisture is fewer moisture decreases. So the presence of heat radiating from flames of a wildfire can preheat nearby vegetation, and the fact that the wildfire can cause preheating of nearby unburned forests, that is the reason why the wildfire can spread easily. So as long as you can properly monitor preheating process in this during this pre-ignition phase, we can pretty much predict where the forest will spread and how much fast they will spread, right? This is the relationship between fuel moisture and fire spread. So as long as we can properly monitor fuel moisture contents, we can also predict fire spread. As fuel moisture decrease, the rate of spread increase. However, this near real-time vegetation fuel condition, fuel moisture. The reason that we say fuel condition is because as long as we can monitor vegetation temperature here, it is also very useful for the prediction of fire spread. So in addition to fuel moisture, vegetation temperature is our great interest. So fuel condition has never been properly provided. Um, Live fuel moisture content, LFMI, like we discussed in previous session, actually they are more specific to chlorophyll content rather than the moisture. And like we discussed, there can be some other reasons for why the vegetation loses the chlorophyll. So of the reason that the forests have reduced chlorophyll contents could include some other reasons, non-drought conditions. And at the same time, they are obscured by cloud and dust and smoke and so on. So vegetation heating process actually can occur within several days. However, this vegetation index actually represent a longer process, like several weeks of change may be expressed by vegetation index. However, a few days of changes may not be properly shown by this vegetation index. So we also briefly discussed about the idea to use land surface temperature as a proxy of um, fuel moisture or fuel temperature variables. However, their force emissivity is often not really measured, and instead they are linearly approximated as a function of vegetation index again, or energy balance equation is used to estimate land surface temperature. They often assume that land surface layer has no heat capacity. And we're going to look at some more details about this idea to use air temperature for monitor vegetation temperature later on in this session. However, if you are using air temperature for monitoring vegetation conditions, they actually have a lower dependency on the vegetation conditions than soil moisture or evaporations. Um, Often people use the assumption that canopy temperature is equivalent to the air temperature or soil temperature. However, for example, in SMOS and SMAP soil moisture retrieval algorithms, uh, however, this is not the valid assumption for heat wave conditions, under which canopy temperature is usually greater than air temperature. So this kind of very important temperature gradient may be neglected if you make such an assumptions. So first, if you would like to use infrared sensors, there are several options that you can consider for the estimation of vegetation or fuel conditions. One option is widely the most commonly used data set would be vegetation index. Like we briefly looked at this option, if you are using infrared sensors, you are going to target these wavelengths in red box, which is shorter than microwave wavelengths. How it works? They usually have some combination from two bands, which is red and near infrared bands. So certain pigments in the leaves strongly observe red, however strongly reflect near band. So if you make a combination, properly make a combine those two bands, then you can pretty much identify and chlorophyll contents, so that you can detect the greenness of the leaves, so that you can infer timing and extent of drought, and which can be related to fire spreads or fewer moisture contents or even evapotranspiration. So if you look, when you are using leaf area index, you can see that after wildfire, shown by a dot line in red, you can see that there's a drop of LAI, so that you can see that the greenness is disappeared because of wildfires. And so it means that LAI can be an interesting tool to monitor the fire occurrence. However, there's a very limited predictability. If you look at the figure here, NDVI did not really show any predictable, um, yeah, predictability before the wildfires shown by the red contour. Yeah. So this region in red contour had a large fires. However, NDBI were just still very green. Yeah. until the fire starts, did not really indicate any fuel information whether this area is vulnerable to fires, and about the fuel availability. The second option that you can think about if you want to use infrared sensors is eco-stress data sets. They indicate some pre-fire hydrological conditions. If you look at the data first here, A shows burn severity, and B evapotranspiration, and C evaporative stress index, and D shows a water use efficiency. So for those burn severity area, elevation of evapotranspiration indicates that the temperature in the given area increases. So so high severity burn area is shown red in figure A, is kind of kind of overlap with the increased evapotranspiration appropriately. And if you look at the figure C, which shows evaporative stress index, which is computed from clear sky estimates. It's a kind of normalizing actual evapotranspiration with some reference evapotranspiration, which is estimated from Penman-Monteith's reference evapotranspiration for the grass. And actual evapotranspiration is retrieved from the surface energy balance. So it's kind of they normalize their evapotranspiration with the reference evapotranspirations to see, whether it is higher or lower. If you look at it in figure C here, evaporative stress index is increasing over high burn severity area in figure A. So which means that similar to figure B in evapotranspiration, evaporative stress index has been kind of increased already as the temperature is increasing over fire or vulnerable area. And similarly, in figure D shows water use efficiency. And water use efficiency is the ratio of amount of carbon fixed per the amount of water lost in the units of evapotranspiration. So for those high severity, high burn severity area in figure A showed very low and reduced water use efficiency. Yeah, because in this area there was a fire occurrence and carbon was emitted rather than carbon fixation. And there was a increase of temperature, and evapotranspiration also has been increased, so it's kind of consistent with other indicator. So for those reasons, fire vulnerable reasons, for the fire vulnerable areas, we can expect that the temperature would increase. Yeah, there's elevation of temperature. Accordingly, there's an elevation of transpiration. Accordingly, there's increase of evaporative stress index. However, the water use efficiency will be decreased. So these indicator kind of show some fire risk, for a specific area. So if you closely look at how they retrieve these variables from infrared sensors, on the right hand side, the eco-stress means ecosystem spaceborne thermal radiometer experiment on space station. They rely on two-source energy balance model suggested by Norman in 1995, and Custas and Norman 1999 and 2000. They consist of two parts, soil and canopy. And Ecostress land surface temperature is being used to constrain a sensible heat. If you look at the box in here, um, yeah, if you can see the box in here, a radiometer temperature will be measured from EcoStrat land surface temperature, thermo infrared sensors. And then as long as they estimate air temperature, which will goes to uh, this equation for sensible heat, and then as long as you determine all other terms for radiation and sensible heat and so on, and then latent heat will be computed from the reservoir. So please note that in here, like we discussed previously, this for the canopy term here, they used a soil temperature instead of canopy temperature. Let me show this here. Yeah. So like we discussed in previous slides, I told you that there's some simplified assumptions to be widely used by SMOS and SMAP and soil moisture retrieval algorithm and land surface and snow hydrology modeling, that canopy temperature is assumed to be equal to air temperature and soil temperature sometimes. However, this is not valid for heat wave conditions and warming conditions because canopy temperature is usually higher than air temperature. However, even in this case, they rely on the same type of simplified assumption that canopy temperature is same with the soil temperature. However, that is not the case for the warming environment. So all these factors actually contribute to uncertainty and errors in the estimation. And the another variable that we can consider for the estimation of fuel conditions is to look at the live fuel moisture contents. In this approach, if you visit this website here, and you can see all the details about this modeling, and they rely on the linear relationship with vapor pressure deficit, as which will be estimated as functions of modest land surface temperature and NDVI. So if you look at the relationship here, it's a function of LST vapor pressure deficit uh, to estimate a fuel moisture. And they also look at the chlorophyll contents from optical sensors, and they also calculate vegetation cover, emissivity, reflectance, and radiance, brightness, temperature, and so on as a function of LAI. So these are the parameters that you can get from this modeling. So if using pre-fire live fuel moisture contents, you can see that as on the figure here on the left hand side, as the pre-fire live fuel moisture content decreases, you can see that cumulative bond area increases, right? And if you look at the figure on the right hand side, they try to retrieve this kind of live fuel moisture contents to monitor and evaluate burned area. Um, So they retrieve fewer moisture contents from the relationship that we have seen in the previous slide. Um, uh, and they try to plot their estimated fuel moisture against observed fuel moisture. The relationship is kind of scattered. I think possible reasons are because this kind of photosynthesis and the use of NDVI and LAI may not really thoroughly directly reflect and represent the moisture contents in the vegetations. Um, if you look at another examples, they also use it fewer moisture contents over burned areas, and they found that kind of their products were affected by the selection of the sensor. So sometimes VIIRS worked fine and nicely correlated with the rainfall, but other times the Moody's product did not really show a correlation with rainfall very well. As you can see in figure D and figure B. Yeah. So limitations of these approaches and some possible discussions will be that reflectance is very complicated. Yeah, it's very complicated. It combines lots of factors from many things. So they are affected by the vegetation structures, some atmospheric conditions, more than pure moisture or vegetation water contents. So although reflectance is high or something like that, that's not something that we can linearly assume that, oh, okay, so vegetation moisture will also be high. That's not something that we can, jump into the conclusion. And the most of the approaches that we've seen so far is based upon empirical approach. So like we discussed in the first session, if you rely on empirical approach, then it may work for the pixels that you establish the relationship. However, it may not work for the other pixels different from the pixel that you carried out your validation and calibration study. And it will be difficult to expand this kind of empirical approach to large scale. And we also, as we also discussed in the first chapter, if you're using this kind of empirical approach, and they may represent small scale, however it will be difficult to apply to a larger scale because there's a nonlinear effect from in the larger scale wildfires. And large scale observation is not something that we can conveniently extrapolate and extract from rearrangement and composition of point measurement or small scale measurement. And also, if using a vegetation index information, there is a saturation problem, which means that although like fewer moisture or fewer temperature increase or decrease, there is no change in vegetation index, not really sensitive to any change. And it is difficult to apply to forest means that although like the vegetation index in that you have calibrated or applied to the cropland agricultural lands may not be directly transferred to forests because forest has the trees in forest they are like 20 meters tall, like sometimes like 30 meters tall, and very packed. They're in more densely distributed area, but sometimes their NDVI or LAI index is very similar to croplands in with like 2 meters high of crops or 1 meters high wheat and so on. So although their vegetation height and vegetation structure, their density are very different, their resultant vegetation index may uh, remain just same. Yeah, does not really differentiate forest from the croplands. And if using like vegetation index or land surface temperature from sensible for infrared sensors, they sometimes have very weak relationship with fuel moisture contents. And they also does not really differentiate from non-drought cases, yeah, due to disease or pest or aging or flushing.